And hello everybody, welcome back to our learning journal on radiation. And of course, yes, mic is working, very good. Just gotta check, if not I'll be recording for no reason. So, thanks. Yeah, you want to realize something, that for a thermal equilibrium, for body, any kind of body in thermal equilibrium, we find that the amount of heat being absorbed and the amount of heat being emitted is exactly the same. So according to this textbook, it references Kirchoff's law here. So what is Kirchoff's law? It's the same guy who does a lot of the other electrical circuit laws, but this is what Kirchoff's law says. For any this is from Wikipedia, so I'm not going to bother. It's a very quick search on Google. It says for any arbitrary body absorbing and emitting thermal radiation in thermodynamic equilibrium, emissivity is equal to absorptivity. So, okay. So in thermodynamic equilibrium, only radiation heat transfer. Okay, if you have this sort of a case, then you'll have the absorption equals to emission. But what again? Yeah. So this is what is being shown here, where in a black body the absorption and emission are exactly the same. If this is in some thermodynamic equilibrium with, let's say, this surface, this red color surface over here. So what exactly is absorptivity and emissivity? And emissivity. Okay, so these are some things that we have kind of learned very briefly in undergraduate heat transfer, undergraduate studies of radiation. Well, let's go for a more formal definition. So we're going to go to this book here, and we're going to take a look at, first thing, how do we, before we start defining these terms, absorptivity and emissivity, we need to look at emissive power. Alright, so this is the prerequisite to learning what absorptivity and emissivity is. Okay, so according to this, we can take a look at these what do you call that? These two definitions here. Okay, let's do a copy and paste. All right, do a copy and paste. Very simple copy and paste into this place. All right, how can we think about radiation coming off a body? So let's have an arbitrary, oops, it's really small. Let's have an arbitrary surface, and then it's emitting some sort of radiation. Okay, it's at some temperature T1, or let's just say some temperature T. And how do we characterize? How can we characterize the radiation coming off the body? So what is the radiation dependent upon? What are the factors? One thing we can look at is direction. All right, directionality is important, because sometimes you can have, let's say, in the case of a laser, okay, in the case of a laser, or a lot of radiation is being shot off in one direction, right? In the case of a flashlight, it's just slightly more diffuse, right? Radiation is coming off like that. All right, in the case of a lamp, a heat lamp or something, you have radiation moving off in many directions. It is more diffuse. So it can be like focused in one direction, or it can be diffuse. So these are some of the factors. That's the first factor. Second factor is that, okay, we know that the radiation coming off a body, it may not be of a single wavelength. For example, let's take the sun, the surface of the sun. You will have UV, all right, UV. You have gamma radiation. You have light, visible light, and you have heat as well, and etc. etc. You have microwaves. So you have microwave, radio wave, the whole spectrum, electromagnetic spectrum is there for you, and it is being emitted from the surface of the sun. Okay. So the other thing that's very important for us is frequency. Okay, frequency or wavelength. So frequency of the electromagnetic spectrum is very important. Okay. So these are the qualitative things that are involved. Okay. So of course, time is very important. You have power per unit time. So yeah, of course the temperature, depending on the temperature, you'll have a different frequency distribution. All right, so these two kind of have to be taken into account when it comes to the heat flux being radiated off the surface. And of course, if you have, let's say, a small surface area here, it kind of captures less radiation. If a larger surface area here, it will capture more radiation, and therefore it will capture more energy. So, yeah, that's very important to account for as well. It's called the surface area. Okay, so this is what this thing is talking about. We define radiation as such. The spectral emissive power. Okay, so spectral emissive power is the EV here. EV equals to energy per unit time, per unit area, per frequency. So if we integrate across all frequency. All right, so you have E equals to integral across all frequencies. Okay, I think I should replace this by a nu instead of a V. Okay, you have E nu, the nu. So you integrate across all frequencies. Okay, or maybe I should put integrate 0 infinity. Yeah, so this is how the relation is between total emissive power and spectral emissive power. So this thing kind of integrates the energy and doesn't consider what kind of frequency this energy comes into. So these are the first introduction to definition of how we deal with radiation. So all right, a few more interesting subscripts we need to take note of. Some special cases, all right, of again, we have radiation coming from the emissive. Yeah, so basically we have radiation coming off a body, and we know that it has a certain frequency to it. So what is the how can we describe radiation that's of particular frequencies? Okay, so now we talk about spectrum, because we are going to go towards black body emission and how the spectrums look like. This is the most simple case, I guess. Okay, spectral emissivity. So what are some of the special cases? All right, Of course, black body is one. We kind of talked about that. The other thing is what we call monochromatic. All right, monochromatic. Monochromatic means one color or one frequency. So this is a very special case. For example, you have a laser that's emitting red light at some particular wavelength only. We call that monochromatic, or else monochromatic or single frequency. Single frequency radiation. So and what else? We can also talk about gray. That means energy is equally distributed across all frequencies. So this is some of the nomenclature that's being used in radiative heat transfer studies, and this is basically how we define some of these special cases, some of these special spectrums. So monochromatic means you have only one frequency that all the energy is being focused into, and gray is the special case where you have energy equally distributed across all frequencies. Like, may not be realistic, but in certain cases it's a good approximation to have, and it's mathematically pretty simple to handle. Okay, I'm gonna stop here. So in this part we only covered a little bit about emissive power, spectral emissive power, alright, and total emissive power. And we wanted to take a look eventually into absorptivity and emissivity. So first thing, we look at the simplest case. It's called a black body spectrum. So we went through some of the definitions, and next thing we want to look at is what the black body spectrum looks like. So this again, we are starting from the most simple case. We are going through definitions, then we are going to look at the simple case of black body. Then we can take a look at more complicated cases later on. So thanks for watching. I'll see you guys next time.